Everyone's like, I'm not doing any parts, and I was like,
Okay, this first one up here about pressure in a canister, helium and argon. If the pressure is 9 and there are two gases, helium and argon, argon's providing 3 atm. How much pressure is the helium providing? 6 atm. Because it's the pressure of the helium plus the pressure of the argon equals the pressure total. And so if that's 9 and that's 3, then that guy's got to be 6. You can see that. All right, that's better. Talking about the same canister, I've got 40 grams of argon. Okay, so there's 40 grams of argon. I want to know how many grams of helium that there are. Is it 80? What's providing the pressure? The amount. When you say amount, what do you mean? The number of particles, right? They're both in the container, same container, so they're both at the same temperature. So one of them is providing a greater pressure, double the pressure, because of what reason? What do you mean by size? No. Somebody said something else back there. Twice as many. That's it. There are twice as many particles. The reason that the helium is at 6 atms and the argon is at 3 atms is there are twice as many helium particles. Okay, so I have 40 grams of argon, and argon's molar mass is about 40 grams per 1 mole. So how many moles of argon are there? There's 1 mole, about 1 mole of argon in here. So how many moles of helium are there? So that leads you to 2 mole of helium. And for every 1 mole of helium, it's about 4 grams of helium. So 8 grams of helium. So whoever said 8, you're right. Why is it not 80? Helium's a lot smaller, and it's not about the size of the particle, it's about how many particles there are. So you needed to figure out how many moles there were of each and compare the two of those things. All right, a gas occupies 927. What's its volume at 132? So what's the first thing you want to do? Change it to Kelvin. 273 to 300K, 273.504K. Great. So what did we do to the temp? The temp went up. So if I had a container of gas in a variable size object like a balloon, and I increase the temp, what would happen to the volume? Go up. So I'm going to start with 900 milliliters here, and I'm going to put 405K on top, and I'm going to put 300K on the bottom. The K's both cancel out, and I'm just left with milliliters. So I get 1,215 milliliters. So you're probably right, 1,220 milliliters with correct sig figs. Determine the pressure change when a constant volume of gas at 1 atm is heated from 20 to 30 degrees Celsius. So what's the first thing you want to do? Switch it to Kelvin. 273, 293, 273, 303. So it's in a basically maybe like a steel container, It's a fixed size container. We don't have a balloon this time, and the pressure is going to change. What did I do to the temperature? I raised it. So what would happen if I took a aerosol can and threw it into a campfire? It would not expand. No, it would not. The pressure would go up. It's a fixed size container. The container size is not going to go up. The container is going to be that size. The gas's pressure on the inside is going to go up, and then it could exceed the pressure and then split the can. But regardless, the can size isn't going to change. So what I have here is a canister that's size isn't changing, and I'm increasing the temperature of the gas inside the container. What's going to happen to the pressure inside the container? It's going to go up. So I've got 1 ATM and 303K and 293K. $1.03 ATM. Final volume, 300 milliliter gas that's subjected to a temperature change from that to that. The pressure changes from that to that. Okay, so what we're looking for is a volume. We've only got one volume unit up here, so let's go with that. I've got 300 milliliters. So I'm going to start off with this. I'm going to have 2 railroad track. I'm going to end up with milliliters. What should I have done first? 273, so 323K and what is that? 285K. All right, so the temp went from 12 to 50 degrees Celsius. What would that do to the size of some gas if I heated it? It would get bigger. So I'll put the bigger number, the 323 number up top, and then the 285 number on the bottom. Cancel out the K's. I also took the pressure of this container and I changed it from 750 millimeters of mercury to 360 millimeters of mercury. So I reduced the pressure on some gas. What would that do to the size of the gas? All right, got bigger? We're okay with that? Yes? Have this container, and the container size can change, and I reduce the pressure on the container. What's the container going to do? I have a basketball, and it's at the bottom of the swimming pool, and then I release what's ever holding it there, and I let it go up to the top of the swimming pool. What's the basketball going to do? It's going to expand. It's going to get bigger. So I'm going to put the bigger number, 750 millimeters of mercury up top, and the smaller number, 360 millimeters of mercury on the bottom. Cancel that out. Times 323 times 750 divided by 285 divided by 360. 708 milliliters. Find the volume of 2.4 moles of helium gas whose temp goes from 50 and it's 2 atmospheres. Okay, so what am I looking for this one? I'm looking for a volume. Are there any volume units there? Can I get any volume units out of what I got? Not what I got up there. So what isn't shown that I need? No? I need that. Does that make sense? So how did I know that I needed to use the ideal gas law constant? How is this problem different than the prior 3 problems? There's no volume when I need a volume. What else? There's no before and after.
Oh, yeah.
There's no initial temperature that's changing to a new temperature. There's no P1, P2, T1, T2. Nothing is changing. It's just these are the conditions. Tell me what's going on. So in that case, you're not going to use one of the Boyle's law, Charles' law, Gay-Lussac, or Avogadro's law. You have to use the ideal gas law. So I was looking for a volume. So I set this up with my volume unit that's in the numerator. And now I just need to get rid of all the other units that I don't want, the ATM, moles, and K. So I'll put 2.4 mole up top so I can cancel that out. And then I'll put 2 atmospheres in the bottom so I can cancel that out. And then I need some temperature. So 50 and 273, 323K. So then I'll put 323K in the numerator so I can cancel that K out. And then the only thing I have left is liters. 0.08206 times 0.4 times 323 divided by 31.8 liters. Okay. The next one. I'm looking for a volume here. Do I have any volume stuff here? Nope. There's no volume up there. Are there any before and after? Nope. So I'm using ideal gas law. There's one problem with this, though. What's the one problem? What about it? I need to know, I've got 32 grams of NO2, and I need to know how many moles of NO2 there are, but that's not really a big deal. So in this case, I'm looking for volume, so I'm going to set this up the same way that I had before. So 0.8206 liter atmospheres, mole Kelvin, and I need to get rid of everything except for the liters. So I'm going to put 312 ATM on the bottom. This is 273, 9, 2. So I'll put 291K in the numerator so I can cancel out that K. The ATM already canceled out. I need to cancel out the moles. I don't have any moles up here, but I do have a gram number, and I can go from grams to moles. So I'm just going to write 32 grams of NO2 right here. And then I can write 1 mole NO2. And then, what is it? 14.007 plus 15.9994 times 2. So this is 46.0055 grams. So then my grams canceled, and then I just have my mole, which will cancel. All right, so I've got 0.08206 times 291 times 32 divided by 46 divided by 5.32 liters. And then the last one down here is how much faster would CO2 escape from a container than UF6? All right, so the equation is rate 1, rate 2, square root molar mass 2 divided by molar mass 1. I'm going to put the smaller one as rate 1, so that'll be the CO2. So I've got 12.01 plus 15.9994 times 2. So in my denominator here, I'm going to have 44.0098. And in my numerator, got 238.0289 plus 18.998403 times 6. And so that's 352.019 square root. Divided by so the CO2 is going to escape 2.8 times faster than the uranium-6 fluoride is going to escape.
So is rate the unknown in that case, then? That's what we're talking about. Okay, so you just, okay, that's something.
Because we're looking for faster.
Got it.
Plus, where would you get a rate number from?
That's what was confusing.
So when I'm looking at that equation, really what I'm trying to do is calculate rate 1, because the rate 2 in the answer is going to end up being the number 1. So what do these two numbers mean then? This 2.8 and this 1.
2.8, well, this maybe 1.
So whatever rate the heavier gas is moving, multiply it by 1. Whatever rate that is, you multiply it by 2.8, and that'll tell you how fast the slower gas is moving. So if my uranium hexafluoride is moving at 200 miles an hour, how fast is my carbon dioxide moving? $480? That sounds right. 560. So if I know what the rate of the heavier gas is, I just multiply it by whatever this value is. What if I know the value of my CO2? What if my CO2 is moving at 300 miles an hour? Then I divide it by 2.8, and that'll tell you how fast the heavier gas is moving. Yep. That's it.
Can you say it last